Good morning, everyone. Uh, in the last series of lecture videos for the control system, we have described about the mathematical modeling of the system and the time response of the system, block diagram, signal flow graph, and all these things. So, from the concept of the preliminary basics of the chapters we have already discussed, it is bit clear that whenever we are talking about any system, that means we write it in the form of transfer functions, say maybe gs, maybe hs, maybe other terms like this, and that is a function of Laplace. That means this is your system, and any kind of input is applied, you are going to get corresponding output. Now whenever you are writing like gs or hs, whatever, so always that means there is a physical system acting behind it, right? Maybe your mechanical system, maybe electrical system, maybe pneumatic system, maybe hydraulic system, maybe thermal system, whatever. So modeling of it gives you this kind of transfer functions, and this kind of transfer functions is normally specified by its order and type. Either it may be first order, second order, third order, it may be type 0, type 1, and type 2, so on, right? So once the system is designed, so next part, one of the most important part of any system is that you want to get a stable system, right? So the system may be open loop stable, or maybe there is kind of you may add some feedback part with it. You may add some feedback path to this system such that this will be the closed loop system. So ultimately your aim is to get C by R. That means either this is open loop transfer functions or closed loop transfer function. These are the notations or the terminologies you are already aware of. So our aim is to get whether the system is stable or not. If the system is not stable, that means you are not going to get the desired output, not the system is valid in real life. So that means in any way, either the system is open loop stable, or either any kind of feedback you can add to make the system stable, or there are different kinds of controllers you can add to make the system stable. So basically our aim to design a system which is a control system must be stable in the sense the output can be your desired value, the steady state error is very less or nearly equal to 0 for different kinds of input like step input, ramp input, and impulse input, and the parabolic type of input, whatever the different types of inputs can be available, as we have already discussed in time response analysis, right? So basically, yeah, in case of stability, roughly speaking, there are we can say that the two notions normally in general case there are normally two notions. But the notions is that first of all, so if you apply bounded input, if you apply bounded input, so RS is bounded to any system. So this is your system. You should get bounded output, right? That means CS will be bounded in nature. That means if you are going to get the bounded output of any system by using or applying a bounded input, so that system is said to be stable, and that stability is known as BIBO stability. BIBO stability means bounded input, bounded output. I repeat, if this input is bounded, then if the output is bounded, system is stable, but provided the input must have to be bounded. If you apply any unbounded input to any system and corresponding to that you are getting say bounded input output, so that can be stable. But if you can apply bounded input and you are getting unbounded output, the system is said to be unstable system, right? So this is the first notions of roughly speaking, that the stability can be defined like this: if the bounded input is applied to any system and you are going to get the bounded output, the system is said to be bounded input, bounded output system, that is the BIBO system. And Number two, the notions two is like this. If you remove RS, that means input is off and there should not be any output. Like for any system, it may so happen that you have switched off your input. That means no signal is going to the system, but you are going to get certain value of output, maybe very small. So that is not the definition of the stability in broader sense. That means if there is no input, so output should be also off. That means if R is equal to 0, certainly CS must have to be 0. So these are the basic two terminologies or two concept of generalized stability of any system. That means the system must have to be bounded input, bounded output, and if you remove the input, the output must have to be 0. That means if input is 0, there should not be any output, right? So that is the concept of stability, but this concept of stability is valid for only linear time invariant system, right? LTI means this is linear, this is time invariant system. Linear time invariant system already we have aware of. Now linear system means it follows the principle of superpositions, and if the system is not linear, you see this kind of BIBO stability cannot be applied. Say for example, in non-linear system is considered. Non-linear system means its output versus input equation, say y is equal to x square, and if y is equal to mx kind of relationship any system is following, that system is said to be the linear system, and this kind of system is known as non-linear system. There are so many objects or the systems are available in nature which are normally non-linear in nature. So everything we will discuss in our course till this concept of stability, route Hurwitz criteria, and time response analysis, and all these things already we have discussed are related with the linear and time invariant system. So linear system means this will be followed, but in case of non-linear system this may not be followed. So we will concentrate our analysis for linear system. Okay, so but we have called that bounded input, bounded output system stability, right? So this I will just give you some analysis how this bounded input, bounded stability can give the relationship with the pole locations of this GS, that means your transfer functions, right? Say any system is given, this is your GS, that means the system described in Laplace domain, and here you see there is an input RT and output YT. Already this time domain analysis we have discussed, that means any signal is normally function of time. So you know, if this system is given to you and say this system is unknown, for example, now if you apply RT is equal to delta T. What is delta T? That is your impulse. So corresponding to that, what you will get, that is output, is known as response. Okay, any output is known as response, that we know. So if RT is delta T, then YT is known as impulse response. What we get? This is your impulse response. Now this system, this is one unknown system. Now RT may be step, maybe ramp, maybe impulse, maybe any kind of signals, whatever may be the different kinds of signals available, all kinds of signals can be RT, and corresponding to that you may be getting different kinds of output. So to judge the system, first of all what we do, we apply here delta T, that means the impulse signal is applied, corresponding to that what you get, that is known as impulse response, and this impulse response is denoted by GT. Okay, so impulse response of any system is denoted by GT, and if impulse response of any system is denoted by GT, then the relationship in convolution domain, you know this, the convolution sum, convolution domain, what we get, say yt, that is output, yt will be equal to t is equal to 0 to infinite, and g t r, sorry, g tau r t minus tau d tau. This will be tau is equal to 0 to infinite, and so this is the relationship between the output, input, and impulse response. That means impulse response is known to you. Impulse response is known to you means what? First of all, if we apply impulse signal to any system, corresponding to that you get the output, that is known as the impulse response. And once the impulse response is known, then for any kind of input, now this is the relations how you can get the output. Once this is known to you, so any kind of input you can apply. This is your input, you can apply any kind of input, corresponding to that you can get any kind of output, right? So now our aim is to get the condition for BIBO stability, right? So BIBO stability, what does it mean? This means if the input is bounded, that means RT, mod of RT is say finite. Bounded means its magnitude is finite. This is the definition of the bounded. Bounded means its magnitude is finite, not infinite. So if this RT is equal to mod of RT is equal to M, definitely RT minus tau, this will be also some finite, say M1. So this is again a finite quantity, right? So this is our actually the integration formula. So if you take mod on both sides, that means we have to get the output whether this is a bounded or not, or if this is bounded, so what should be the conditions, and which condition, if input is bounded, output will be also bounded, right? So if mod of yt, we get like tau is equal to 0 to infinite g tau r t minus tau d tau. So this, and you know the relations, if this is definitely less than equal to integrate, that is 0 to infinite mod of g tau r t minus tau d tau, right? So this is your relationship, and once this relationship is obtained, then I can say that we can say y of t mod of this less than, so integration of 0 to infinite g tau less than r t minus tau, that is valid. So you see this is finite quantity. So if this is finite quantity, so definitely this is m1, and integration 0 to tau, sorry, 0 to infinite mod of g tau d tau, this is yt. Now according to BIBO stability, now coming to the point, this is BIBO stability, that means input is bounded, we say. Now if output is bounded, so y of t must be having some finite quantity, right? So if this is a finite quantity and this is less than this, so definitely say this is n1 less than m1 0 to infinite g tau d tau, or you can say like m1, just if you say t is equal to 0 to infinite gt dt. What does it mean? This means this should be definitely finite. In order to have this is finite and this is finite, so the relationship between these expressions, from the expression what we get, this t is equal to 0 to infinite mod of gt dt is equal to finite. So this is the condition for BIBO stability. What is this? This is the integration over the area. Say for example, mod of GT. What is this? Mod of GT means the area and dt, that is the absolute value. Say for example, this is your absolute value of impulse response. Now area over the limit 0 to infinite. If you consider the area gt dt integration, that is the area. So if you consider this area, that must be finite. If this is finite, then the system will be BIBO stable. That means if this condition is satisfied, this condition to be satisfied. If this condition is satisfied, then if you apply the bounded input, then only you are going to get the bounded output, right? So this is related to the impulse response characteristics, right? And impulse response characteristic, say GT, normally if you take the Laplace transform of get, you get G of S, right? So GS is your transfer function, as you know. If the transfer function is given to you, then from that what you can get? You can get the inverse Laplace transform to get the GT. That means this impulse response and its characteristic is depending upon the system transfer functions, that is known as GS. And if the system transfer function is known to you, which plays major role is that the pole of the system, right? So the locations of the poles will be related to the conditions of g tau d tau. That means, say for example, we are considering a GS is equal to 2 by S plus 2, right? This is a you see the transfer function of any first order system. So from there we get the poles. What is the pole location? S is equal to -2. That means this is the real value. As we know, this is complex quantity. That means it may be having some real value as well as some imaginary value. And we see from the previous discussion, that is your S plane, Laplace plane. This is real axis, this is your imaginary axis. So S is equal to -2 means this is your 0, so -1 and -2. Here is the location of your pole, right? And if you just divide the total S plane, this is your S plane, real plane, imaginary axis. So this is the imaginary axis, and this side I will write it like, say, complete right hand side of the S plane. That means this is your 0, this is up to infinity, this is infinity, this is minus infinity, this is minus infinity. Real values, that means this is plus of j infinity along this axis minus j of infinity, this is real value of infinity, this is real value of minus infinity. So this side indicates the complete right hand side of the S plane, right? Similar to that, if you consider the left hand side, we will be having, this is the left hand side of the S plane, and in between these two there is an imaginary axis. That means how these pole locations are actually varied over this entire S plane. So we have considered this example. So S is equal to -2. Where is this locations? That is somewhere here. You can get the locations of S is equal to -2. That means that falls in the left hand side of the S plane, right? And if the transfer function is, say, GS is equal to 4 by S -2, what happens? The pole you see at S is equal to +2. That means this pole is somewhere here on the right hand side of the S plane. That means, you see, if the system is like given like this, say 2 by S square plus 2, that means there are two poles, right? This is a second order system. So poles, you solve it, S square plus 2 is equal to 0, you get S is equal to plus minus j root 2, right? S square is equal to minus 2, so root over of that imaginary, that means one pole as plus j root 2, one pole as minus j root 2. So what are the locations? Say maybe one is there and one is there. So we have considered the three examples, right, where you can see the pole may be on the left hand side of the S-plane, pole may be on the right hand side of the S-plane, pole may be on the imaginary axis, right? So these are the pole locations or the roots. Basically these are known as the poles or roots which characterizes the system, because you know the characteristic equation already we have discussed. Now you see these are the actually locations of the poles. Locations of the poles means, so from this actually by inverse what you get? You get the impulse response, and we know system is to be stable when this gt dt mod of this is equal to finite. So finiteness of this integration is very important, as you have already derived. Once this will be finite, then the system will be stable, right? If this is not finite, system will not be stable. So this is actually related to the pole locations, and in broader sense I say the three criteria which will be developed here, right? First of all, the criteria is like this: all the poles are located at the left hand side of S plane. If this so happens, then mod of gt dt integration 0 to infinity finite, right? That means system is stable. So if the poles are lying here in this region, so stable. Next, all the poles are located at the right hand side of S plane. In that case, what happens? 0 to infinite gt dt, this is infinite, right? If this is infinite, the system is unstable, and unstable means the system poles are located on the right hand side. That means if the system poles are located on the right hand side of the S-plane, system is unstable. And third one is that if there are non-repeated roots on the imaginary axis, the system is marginally stable. Marginally stable. That means what? Non-repeated roots. The concept of repeated roots and non-repeated roots. That means non-repeated roots means there may be pole, there may be pole, there may be pole, there may be pole, right? That is, poles are located on the imaginary axis only. The system is said to be marginally stable. So what does it mean, marginally stable? Next, I will show the graph. This is stable system. If the poles are on the left hand side, system is stable. Stable means its magnitude, this is your time, this is your magnitude, its magnitude decreases with time. That means bounded in nature. Bounded means finiteness, right? If the system is unstable, that means its poles, this can be actually said by viewing the pole locations. If the pole locations are lying on the right hand side of the S-plane, system is unstable, and unstable means unbounded system. That means its magnitude versus time, you see, this is like this. That means with time its magnitude is increasing. What does it mean? Its magnitude is increasing. That means this overall infinite, you get 0 to infinite, this integration of this impulse response over the time, integration, that means area you are getting is infinite, right? Infinite area again. This is the finiteness, and you see this magnitude is decreasing with time, and What is about the marginal stable? If the poles are lying on the imaginary axis, but they are definitely non-repeated in nature, right? I say this is non-repeated, non-repeated in nature. So in that case, what happens? Its magnitude is bounded, but not decreasing with time. Like this, like there is a kind of oscillatory behavior. You say oscillatory behavior means this is having two fixed values, either in positive side and negative side, where magnitude actually oscillates, right? So this is the kind of behavior you can observe if the poles are non-repeated and lying on the imaginary axis, and if there is an oscillations, so that means that case is known as condition of sustained oscillation. Condition of sustained oscillation. That means once the system poles or roots are located on the imaginary axis in like this, in that case what will you will get? You will get a condition for sustained oscillations. That means it is oscillating with a fixed frequency. So it will be having frequency at which it is basically oscillating, right? And fourth step is that fourth point, what we like to say, that is if there are repeated roots on the imaginary axis, right? If there are repeated roots on the imaginary axis, then what will happen? If there are repeated roots on the imaginary axis, system will be completely unstable again. So fourth point I would like to describe, that is repeated roots on the imaginary axis. That means structure is like this. That means maybe S is equal to plus J2 plus J2 minus J2 minus J2. That means in a single point you get, on a single point two roots are existing on the imaginary axis, imaginary values, right? So system is unstable. System is definitely unstable, means its behavior or response characteristic is like this, that is magnitude versus time. So its magnitude is increasing with respect to time, that this signal is going to be getting unstable in nature. So there are the four criteria I have jotted down. So I will repeat it. First of all, from the given transfer function, either closed loop or open loop, you have to find out whether the roots are on the left hand side of the spline or right hand side of the spline or on the imaginary axis. If the roots are lying on the left hand side of the axis, that means how can you understand the roots are on the left hand side of the spline? That means if the value of s, you see the value of s is having negative real roots. So s is equal to actually sigma, I can say it, the real value plus minus j of imaginary value. So this can be plus minus. So if the real part having negative value, what happens? Minus 2 plus j4, right? Example, minus 3 minus j4. In these two cases, you see, observe, this is minus 2 minus 3, that means real part. So if the real part is having negative value, definitely in the S plane, if you draw, whether this is plus j4 or minus j4, plus j4 means first of all you have to move negative side along the real axis, so there, and then you have to move in this direction. This is the locations, and here this is the locations. In both the cases, you see they are lying on the left hand side of the S plane, right? So that means if the value of S you get is having the negative real root, so maybe the imaginary value positive, it must be lying on the left hand side of the S plane. So the system will be stable. And in other words, if the repeated roots are there on the imaginary axis, you see again this condition of sustained oscillation, the behavior or nature of the system time characteristics with the magnitude is like this, is oscillating with time, right? So this is the way how the system BIBO stability is the condition is derived, and the condition of the BIBO stability applies to the locations of the roots in the S plane. Okay, in the next class we will discuss how to get the stability using certain criteria, maybe either seeing these locations or maybe either some other criteria like Routh Hurwitz criteria we are going to apply. Okay, thank you.